like to set up they would be able to analyze less than questions. Right? They could defend themselves on these issues. I think let's be honest. Right? We have to ask these things. I understand that the intention is not necessary, right? And that would be risk another change.
Yeah, yeah. Thank you for having me.
Yeah, and again,
Likewise. Thanks a lot. Thank you. Thank you so much for your help.
Of course, yeah, I'm glad. Hi, Mark, can you hear us?
Sorry, say that again. I'm sorry.
All right.
Yeah, I'm here.
Here, okay. I'm gonna stop sharing and let you take over so you can share yourself, and then we'll configure up our
Okay.
sound. We'll plan to have you start about 11.
I'm not showing any charts. I'm just speaking.
Okay. Mark says he's not sharing.
Okay, good.
So the best way to do it is probably just to pin in.
Yeah,
and bring
that
it.
works. Okay.
At the moment, I just see a screen that says meeting host.
Oh, that says me. Oh, wait, can you not see us?
No, I can, not really.
Here, let me stop and restart the shirt because
Okay.
I think sometimes Zoom
Oh,
doesn't.
now I can. Yeah.
You can see us.
Yeah.
Okay, great.
New
Okay.
participants that don't see the share until
Until you.
this is
Weird.
I'm not,
which
not
which
sure
is-
I need to see me anyway, but.
Well, I think everybody in the audience will want to see you. I'm gonna go call them in.
Sure.
So, yeah, I'm gonna go call them in from the coffee break now, so we'll see you in a minute.
Okay.
Mark, I'm here as Nino.
Hey, Nina.
If you need me of anything later on, I can provide you any feedback you want to see from the crowd.
Okay. Do you want me to do any Q&A or just? speak?
I don't think so. You can give your remarks and maybe give a couple of minutes in case they want to ask questions. That would be
Sure.
great. Actually.
Okay.
Oh, we have 10 minutes. Oh, okay, that's right. So you have 10 minutes, Mark. So yeah, you can have you can receive a few questions and
Right.
can help out with the microphone and everything like that. So that you can hear the question. We had some issues yesterday with Janice Lee that people couldn't hear. She also was remote. So I'll make sure that the technology works and you can hear them.
Okay.
Yeah, and you can see in the background. So
My other glasses.
You pointed something so far.
Hey, Michael. I don't really know if anybody's planning this or not. So the answer to your question is that it means national. I would say
Mark, we are waiting for a couple of more people to come in from the coffee break.
Yep, no problem. I was just making my office look a little better. There's lots of packing cases since we just moved back.
All right, should we start? Where's Don? Okay, thank you very much, everybody. I hope you enjoyed what's that?
Getting closer to Mike.
Even closer than this?
Yeah.
All right. Okay. Oh, okay, Don. Thank you very much for be back on time. And I just want to introduce you Dr. Mark Lampin. He's the Astrophysics Division Director, and he's going to say a few words for you all. And there will be a couple of minutes for questions if you have any for him and about all the work that we do in astrophysics. Mark, take it away.
Okay, thank you. So it's really my great honor to address you all today at this 2024 NASA Hubble Fellowship Program Symposium. And I should just say this is the fun part of being the APD director, to get to talk to the next generation of astronomers and astrophysicists. So I think to begin with, it's critical to acknowledge that this has been a tough year and one of significant challenges and also transformations for our field. We've faced some budget constraints and shifting priorities, but I think our community has come through that test and shown that it's both resilient and adaptable. And I think NASA Astrophysics has a really bright future. So let me tell you why, and why you should be really excited about where we're going. So Webb, of course, is continuing to give us great insights into the early universe, for example. And I was just looking a few days ago at a new study by Catherine Chorosky, I hope I pronounced that correctly, looking at early galaxies and finding, in fact, that they're much less massive than we first thought they were when we started looking at them with JWST. And in fact, the black holes in some of these galaxies may actually make them brighter and bigger than they really are. So we're continuing to sort of push and understand, what was going on in the early universe with Webb, which is, for me, who worked on that program for many years, really exciting, because this is why we built it. Another mission that we're continuing to operate and is continuing to produce great science is TESS. So TESS is still finding small rocky planets, and a good example is the recent discovery of GJ238b, which is, a 0.6 Earth radius planet orbiting M2 dwarf star at around 15 parsecs. And again, TESS is doing exactly what we built it to do, which is to find small rocky planets. But one of the things that really amazes me about TESS is that at the moment, 60% of the GI science that it does is actually time domain and multi-messenger science and not studying exoplanets. So it just shows you how adaptable some of our missions are. Now, my top priority, and you should all know this, is to complete the development and then deliver the Roman Space Telescope. And I'm happy to tell you that Roman continues its development. It's on schedule for a 2027 launch. And I'm even happier to tell you that if you don't believe me, read the Inspector General's recent report on Roman, which gives it a clean bill of health. Roman is going to be a really exciting mission. And it's going to be a big change for this community that I'm speaking to now, but also our wider astrophysics community, because Roman will really be the first NASA mission where we put the data into the cloud and you work on the data in the cloud. And this is because Roman is going to produce a lot of data. Now, some of our colleagues in other areas like earth science have been working in this paradigm for many years, but for astrophysics, Roman will be a real sea change in how we do science with NASA missions. I also wanted to highlight a forthcoming launch, SphereX, which is a mission that will conduct an all-sky spectroscopic survey being built by PI Jamie Bock at Caltech, is nearing completion. We're completing the final assembly of the spacecraft bus right now, and this mission is due to launch sometime next year between February and April. And then finally, I have to say something about the Habitable Worlds Observatory. There's a lot of excitement around this, which is the next big NASA flagship that comes after the Roman Space Telescope. And I think you can see how much excitement, not just in our astrophysics community, but also in our stakeholders who help us and fund us to build these missions, have seen this mission in the sense that they have just recently directed us to create a project office. And we got that direction in April. And as of August 1st, that office went operational. So we now have a Habitable Worlds Observatory project office, which is located at the Goddard Space Flight Center. And you'll be hearing a lot more about this mission as we go forward. So I really think we have a bright future. We're doing lots of great science, which comes from lots of really great missions that we're operating, we're developing, or we're just starting to design right now. I also want to highlight the incredible spirit and diversity that's embodied by the 2024 Hubble Fellows. The cohort this year represents a remarkable array of backgrounds, disciplines, and perspectives. And, you know, the Hubble Fellow Program isn't just about fostering individual talent. It's about building an inclusive community of leaders where diverse voices and experience come together to drive innovation in astrophysics and really drive the community forward. So this program has always been about pushing the boundaries of our knowledge. It is a prestigious program and it supports exceptional postdoc researchers whose work really will make a big impact on the fields in which you work. And you will also become the next generation of inclusive leaders in our community. So I wanted to share a few highlights of what I think makes you really exceptional. First of all, you have very diverse research focus. So our Hubble Fellows really are engaged, you really are engaged in a wide range of cutting edge research. Some are using observational techniques to study the formation of exoplanetary systems, for instance. Others are using theoretical models to understand black holes and gravitational waves. The research really covers a full gamut of astrophysics, and it reflects the diversity and breadth of the research that we do in NASA astrophysics. I also think it's important to call out the fact that you're also very innovative, and our previous cohort of fellows have been very innovative in the past. And in some ways, pioneers in their programs, employing new methodologies. I hope this cohort and this generation of Hubble Fellows will start to really use advanced machine learning for the next generation of space telescopes, starting with the Roman Space Telescope. And I also think this is a community that's really very collaborative. So beyond your individual achievements, Hubble Fellows have been contributing to a vibrant collaborative community and engaging in interdisciplinary projects that mentor young researchers and share insights with broader audiences. So your involvement really helps foster a culture of collaboration and mutual support within the astrophysics community. So you really, in my view, exemplify the essence of scientific inquiry, curiosity, determination, and a willingness to really embrace the unknown. So I want to finish up by thanking you for all your hard work, your passion, and your unwavering commitment. And I do want to, take questions from the audience, because I really think that interaction is very important. Unfortunately, I couldn't make it there in person this year, but I really do want to hear from you. And if you don't contact me or ask a question during this session, you are really welcome to send me an email anytime and we'll try and answer your questions. So Nino, do you want to take some questions?
Sure. Let's see. Thank you very much, Mark, for now. Okay, so we have a couple of minutes for questions for Mark. Anybody? Any curiosity? I know some people were interested in how I get a job in NASA, like a permanent job, like a civil servant job. Nobody wants to speak up?
Suddenly everybody is very shy.
Yeah, we have one question here. Let's see if we can.
Thanks for making time to talk to us today. I just had a very kind of high level question, and maybe it's really tough to answer, but what is your take on the current budgetary climate, and what would you have to say about it to some of the younger people in the field, or looking up and looking at people 1, 2 steps about really struggling to put together budgets to hire people and keep the labs running and stuff. So I was just curious if you had I don't know ways of perseverance and wisdom for us.
Mark, I don't know if you hear the question, but it's about do you talk about advices for budget, or how you if you have any suggestions on what's the stress about putting together a budget, and what recommendation you have for early career scientists that might have to think about budget and funding early career researchers themselves in the future, Mark?
So I've worked at NASA for a long time, 20 years. And the one thing that I always tell people when they ask me this question is that, budget cycles are very cyclical. And, 1 year things will be or sound bad. In a couple of years, it's a very different environment. And, despite the cyclical nature of the budget over the years, NASA Astrophysics has built some amazing missions. We will continue to build amazing missions. I've said a number of times that as I look at the budget when we have to make difficult decisions, that I want to balance the portfolio and make sure that we're investing in early career scientists, in early career science. So I think it's important to maintain the RNA program and also make sure that we are developing the next generation of missions so that you, the early career community, can do science in 5, 10, and 15 years from now with those missions, as well as the missions we're currently operating that will still be running then. So I think my advice is, there are always going to be challenges, and we always try to do the best we can to minimize the impact on our community and move forward and do the things that we are recommended to do by the decadal survey, and to make sure that the missions that we're operating are producing the best science.
Thank you. Any other questions or comment? And as we touch upon budget, I want to just let you all know here that thanks for Mark that came on board as a director 2 years ago, that we now have resources, financial resources, to provide you opportunities like the one that you just had, the DI session early on, thanks to Mark's continued support and actually increased support from the past. So that, I should mention this since you are online, Mark, thank you very much for making the program even more impactful.
Thank you.
Okay. All right. Thank you so much, Mark.
Okay.
And we'll continue with the program here. Thanks a lot again.
Thanks, everybody. Appreciate it. Bye.
Hi, can you hear me?
Hello. Hello, Nick. Yeah, you're audible. I'll just begin with an introduction. Well, welcome to the afternoon session, the session that's keeping you from lunch. And our latest installment of all the great ways we are putting that NASA budget to fantastic use to produce really excellent science. So this is a session that's going to cover the IGM, like really large scale. We're going to like touch on galaxy clusters. So there's a lot of like diversity, but we're going to, much larger scales than we touched on yesterday. And to kick off the session, we have Nick Kern, who's a Hubble Fellow at MIT, and he'll be telling us about mapping the universe with hydrogen, and he'll be joining us remotely. So please take it away, Nick. Go ahead.
Awesome. Thank you. And Rohan, I have a timer here. So I'll set it for 12 minutes, I believe. That's right. But thank you. Thanks, Rohan. A pleasure to kick off this session here. Thank you to the NHFP leads. Thank you to the SOC for making the symposium happen. And of course, thank you to Mark. Wonderful. Okay, so I'm going to talk a little bit today about my work in 21 centimeter cosmology, and I'm going to tie it into some of the things we'll hear about over the course of the week. And I'm going to preface the talk by connecting to some of the things that we've heard and we will be hearing throughout the week about new insights into cosmic dawn astrophysics from JWST. So one of the things that we've learned over the past couple of years about the high redshift universe is the fact that JWST is revealing to us for the first time the brightest galaxies coming out of cosmic dawn at increasingly higher redshift. And for everything that we're learning about these galaxies, JWST is raising new questions and new problems. And it is not necessarily solving renization. In fact, the opposite, it's providing more questions that need answering. So one of the things that we're seeing is if you take UV luminosity functions that are calibrated to HST at low redshift, redshift 6 through 8, and you extrapolate that to higher redshift, that's what you're seeing in the solid and dashed lines. What you find is that there is a seemingly overabundance of galaxies at redshifts 11, 12, and 13. And this is puzzling for a number of reasons. There's various explanations that I won't go into because it's active research. There's numerous, some astrophysical, some cosmological. I think Sultan will tell us a little bit about that later in the week. But this is something that's quite surprising. And if you couple that with what we're learning about the ionization efficiencies of these galaxies, at face value, this is also providing a renization scenario that's in tension with other observations at the end of renization, particularly observations that are measuring the neutral fraction at redshift 6 through 8, that's in the lower panel, and the inferred electron scattering optical depth to the CMB inferred by Planck. This is a plot from Julian from Munoz from earlier this year, showing that at face value, JWST would have renization ending way too early. Now, again, there's theories out there for how this can be reconciled with Planck and with Lyman alpha observations at redshift 6. But what I'm trying to get to here is that this motivates us using multiple lever arms, multiple observations, multiple experiments to try to understand the astrophysics of cosmic dawn. Now, conveniently, 21 centimeter, which is what I'm here to talk about, provides us this complementary lever arm for understanding cosmic dawn astrophysics. And that's because at redshift 6 and above, the 21 centimeter line is actually probing the IGM directly. It's probing the neutral hydrogen in its neutral state, okay? And what it's proportional to is directly the neutral fraction. It's proportional to the density of the gas and the temperature of the gas. And specifically the neutral state and the temperature of the gas gives us a handle on the astrophysics, what's going on, what the ionizing and X-ray photons that are being produced by these first stars and galaxies over cosmic time. And I'll show you this somewhat outdated forecast, but it drives the point home quite well. 21 centimeter really is sensitive to the total photon budget coming out of these first stars, whereas JWST is mainly probing the brightest galaxies. And so what you can see is that if you combine constraints, say from JWST and 21 centimeter maps, for example, from the SKA, you'll find that you get much more precise constraints on the faint end slope of the UV luminosity function, right? We know that JWST will not probe the faint end slope, particularly at high redshifts, very well. And so it's this combination which gives us this more complete picture of cosmic dawn astrophysics. And so 21 centimeter, I would say, is as relevant, if not more relevant, than it's ever been. And of course, because it's directly sensitive to the neutral fraction, we're going to be able to tell you not only when did renization end, but when did it start, and then what did it look like over cosmic time? Okay, so this is the power of 21 centimeter at cosmic dawn and EOR. And if you've ever been to a 21 centimeter talk, the question is, well, why haven't we made a detection yet? And this is kind of the grand challenge of our field right now. And the answer is twofold, really. One is, as you might be aware, at low radio frequencies, the diffuse synchrotron emission coming from our own galaxy is extremely bright. It follows a power law distribution out to low frequencies. But it's not just the foregrounds. Really, it's this combination of really bright foregrounds modulated by a complex instrumental response that we don't know perfectly a priori. And because these foregrounds are so bright, we have this dual grand challenge modeling problem where we need to know both of these things to 1 part in 10 to the 5 precision, which is unprecedented in radio astronomy. So we're having to redevelop how we look at radio data to solve this problem, which is kind of exciting. But what we do have currently are upper limits. So what you're seeing here are upper limits on the 21 centimeter power spectrum at the EOR up till about 2022. And over time, what we've done is we're marching down in this parameter space and ruling out more and more extreme models. That being said, we are a couple orders of magnitude away from these fiducial limits. But some of the work that I did during my PhD and my postdoc, my first postdoc, was to lead an analysis from a new telescope called Hera, which you may have heard before. I talked about this last year, in setting new limits at redshift 8 and 10.5. And this was when Hera was a very small telescope. We're almost finished building the entire telescope, but even with a fraction of its collecting area, we were able to set state-of-the-art limits at redshift 8, which were over an order of magnitude improvement at that redshift. And we're currently analyzing more data, and we're going to have some exciting results coming out soon. Now, the question is, okay, we have upper limits. We don't have a detection yet, but we can still do interesting science with them, actually. So one of the things that we did with these limits were to show for the first time that the IGM must have been X-ray heated by redshift 8. And interestingly, there's lots of theoretical models of cosmic dawn astrophysics that are perfectly consistent with the CMB, with Lyman alpha emissions, and with UV luminosity functions that have the IGM remain really cold at redshift 8. And Hera was able to show, no, the IGM must have been X-ray heated by this time. You can turn that around and say, well, we have some constraint on the sources that actually emitted those X-rays. And if you assume that those X-rays were generated by a high-mass X-ray binary population, we were able to show that this population must have been lower metallicity than their modern analogs. And that's because their X-ray productions were much higher than modern analogs. And this is the first time that we've ever been able to say something about this very high redshift X-ray sources, at least to this degree. So, like I said, there's more data being taken. We're currently we currently will be observing our most sensitive data set to date. This will be pushing not only to deeper sensitivities, but to higher redshifts, where we're going to be able to explore much more complex IGM heating models, which is quite exciting, up to redshift 15, 20, and above. Okay, but the next thing I'd like to talk about in the last couple of minutes here is some of the work that's ongoing for me, which is trying to understand how do we go as a field from just upper limits to a direct detection, because that's really where a lot of the exciting science comes from. And this is a complex question. To give you a sense for how we're thinking about this, I'll motivate kind of the foreground problem. So if you look at the power spectrum of our data, this is a kind of theoretical mock power spectrum, as a function of Fourier wave vector k, you can think of it as having foregrounds in blue, noise, which is Gaussian thermal noise in orange, and some underlying unknown a priori EOR signal shown in green. And what we do currently is something called foreground avoidance, where we say, okay, we don't think that we can model these foregrounds to 1 part in 10 to the 5. So we're just going to cut that data out. We're just going to ignore that data. And we're going to look at the higher K modes where we think there's a clean measurement between EOR and noise that we just need to integrate down by taking more data, taking longer exposures. Now, the problem here is that systematics spoil this entire story. So any kind of systematic, like a chromatic beam response, a chromatic front-end response, radio frequency interference, it takes this blue curve that was nice and compact in Fourier space, and it spills it, and it widens it in Fourier space. And so now if we were to take measurements of this red curve, we might place measurements like this. And you would see, okay, we're detecting some systematics at these intermediate Ks, and then at high K, we measure an EOR signal. But again, we don't know these things a priori. So we might say, well, okay, we know that there's a little bit of systematic leakage, and we see this in data already, that there's systematic leakage like this. So we're just going to cut out more of our data, right? And that's what we do right now. And you can tell, as I'm kind of hinting at, this is a little ad hoc, right? When is enough enough? We don't actually know this right now. And this is where we're at. We can set upper limits like this, but we can't actually make robust direct detections doing this. And so the question becomes, can we do this more robustly? In other words, can we actually just set covariant error bars in our data that not only account for noise, because noise is pretty easy to do. We know how to do noise quite well. What we don't know how to do is to propagate uncertainty from our foregrounds and our instrumental uncertainty onto our signal uncertainty. So in other words, can we explore the joint posterior distribution between all three components of our model? We haven't been able to do this. So this is what I've been working on. And this is now tractable with advances in machine learning software and hardware. So I've built the first end-to-end Bayesian forward model for 21 centimeter. It's called BaseLim. And I won't go through this in too much in detail, but in a nutshell, you take all of your parameters that you'd like, your 21 centimeter parameters, your foreground parameters, your systematic parameters, and you push them through a full-blown data simulation, which typically would take tens of thousands of CPU hours. You make mock data, you compute a likelihood, and you include any kind of priors you have on your model. This could be from measurements of our beam. This could be from other measurements of the sky from different radio telescopes. And you make this differentiable using tools like TensorFlow or PyTorch, and then you optimize and sample from this space. And this is really only made tractable because of high memory GPUs, which dramatically accelerate this process. And so without going into too much detail, I'll just show you the first major proof of concept that I have for this, which is a full Hamiltonian NCMC sampling of this joint signal foreground and instrumental space. And what you're seeing here is this is just a single MCMC chain walking through this joint posterior space, and you're just seeing the response of the EOR signal on the sky. And so these are fluctuations in the EOR map that are fluctuations due to our uncertainty in the beam and the foregrounds. And this is the last two slides here is to show this proof of concept. If I were to simulate a mock EOR power spectrum shown in green, and I were to use this framework to optimize to the maximum a posteriori estimate, which is shown in black, I know on the right, I'm going to be noise dominated. We know this pretty well. And I know on the far left, I'm going to be foreground dominated. And the question is, where in the middle can I actually trust? And so if I show you a ratio plot, if I divide the black by the green, I get this kind of estimated power spectrum relative to the true power spectrum. And we, like I said, we know how to do noise error bars. And so what you're seeing in red is this noise error bar. What we're now able to do for the very first time, we've never been able to do this, is to plot a noise error bar and a foreground and instrumental error bar. And so really it's the sum of these error bars in quadrature, which is what we would use for a full error bar estimate. And indeed, you can see there's somewhere in the middle here where we feel like we have lower total uncertainty. And these would be the modes that we would actually trust in a direct detection analysis. So I'll leave you with that. I have a couple minutes left, but suffice to say, with state-of-the-art upper limits, we're already beginning to narrow down some interesting IGM physics as cosmic dawn with Hera. Going forward, we're going to be analyzing data that's going to push down to deeper sensitivities and higher redshifts, opening up the constraints on much more complex heating models. And we're also working on technology that's going to allow us to make that next big step to actually make a first robust direct detection with telescopes like Hera and eventually the SKA. So it's exciting times, and I'm happy to take questions. Thank you.
Thank you so much, Nick. We have time for one quick question while Michael sets up his talk. One quick question for Nick. Yes, go ahead.
I worked at a photography here.
You just go for it. I was kind of really.
Hi, Nick. Great talk. This is Jared Gusay, fellow, also working on differential models for optical models. And I was just sort of curious if you notice a particular, if you have different algorithmic differentiation packages, and if there was one that was particularly like performative for the work you're doing.
I'm sorry, it's kind of echoey. I don't know if Rohan, if you can just briefly restate the question.
Yeah, the summary of the question was, is there an algorithmic differentiable package that you particularly find more performant?
Yeah, specifically, they brought up TensorFlow and PyTorch, but if there were others that were tested and if one was better than the other.
Right, like compared to like TensorFlow or PyTorch, is there
Yeah.
anything?
Yeah. I would say they're all, honestly, they're all very similar. They're all, I use PyTorch. TensorFlow is somewhat deprecated. I would choose between JAX and PyTorch. Honestly, it's really more, it's not so much the backend, it's more about how the implementation. A lot of the bottlenecks are not due to fundamental PyTorch deficiencies. They're how I'm constructing my model and how I'm choosing to optimize it. And it's literally, there's dozens and dozens of ways to do this. So happy to chat more offline if you'd like. But PyTorch, you can't go wrong with either JAX or PyTorch. Yeah.
Thank you so much, Nick. Let's thank Nick again. Up next, we have Michael, who's the new NASA Hubble Fellow at the CFA. He'll be telling us about AGN feedback in galaxy clusters.
Great, thank you, Rohan. Yeah, I'm really happy to be here for my first Hubble Symposium, hearing all your incredible science. And I'm excited to tell you about some of the work that I've done, not as a postdoc, because I've only been a postdoc for a couple weeks, but I'll tell you about some of the work that I did during my PhD, which is on the evolution of the AGN feedback cycle in galaxy clusters. Right, so I'm largely interested in how feedback processes shape galaxy evolution on larger scales. So we heard yesterday a little bit from Cassie and Shanskriti about the CGM, so I won't dwell too much on that, but briefly, so galaxies we know are not closed boxes. They evolved by mergers, creating bigger galaxies, and also by exchanging material with their surroundings, these inflows and outflows, and what we call the baryon cycle, exchanging that material for CGM. And a lot of this, inflows and outflows are driven largely by feedback processes. For example, supernova feedback on really small scales, and in large galaxies, feedback from supermassive black holes. So that's what I'll be focusing on. So this is the realm of galaxy clusters, which I'll introduce now. So galaxy clusters, as the name implies, are clusters of galaxies. There's hundreds of galaxies in these systems, often dominated by one brightest cluster galaxy, this BCG that we see here at the center. Yeah, this is weird. The BCG here, we see here at the center. And so there's lots of galaxies in these systems, so you should expect there to be lots of mass, right? But maybe surprisingly, most of the mass in these systems most of the luminous mass in these systems is not inside the stars that you see in those galaxies, but rather in the space between the galaxies, which we call the intercluster medium, or the ICM. Right, so this ICM, the important point I want to make here is that it can be thought of, the inner part of this ICM is a CGM of your brightest cluster galaxies. So this is the atmosphere these galaxies are interchanging material. And so this makes this CGM, this inner ICM, glows in X-rays, and that's something that makes galaxy clusters one of the best places to study this baryon cycle in large galaxies, because we can see it in X-ray, you can see the CGM in emission, right? And importantly, these X-rays are given off the reactive cooling process like Bragg-Strömling radiation. And what's important about that is the flux we see from these ICM photons is proportional to density and inversely proportional to temperature. So when you're looking at these galaxy clusters, as you go, look at this image here on the right, as you go towards the BCG at the center, I'll just point to instead. As you go towards the BCG, the center, the X-rays get brighter, right? So what this is telling you is that as you're going towards the BCG, you're getting colder, denser material. So by virtue of sitting at the bottom of these really deep gravitational potentials, BCG should be the bluest, the most star-forming galaxies in the universe because they have all this material being funneled onto them, right? But in reality, what we see is that BCGs are what we call red and dead. There's really yellow, passively evolving elliptical galaxies that aren't doing very much star formation at all, or so it would seem. So this is what we call the cooling flow problem in a nutshell. So if you take a bunch of BCGs and measure the star formation rates inside of them, and then we were to measure how much gas is cooling out of that hot halo, the ratio of those two is about 1%. So only about 1% of that cooling material is making it onto your central galaxy. And so cooling is being suppressed by 2 orders of magnitude. And the consensus the community has come to in the past couple of decades is that this is some heating source at the center of the galaxy called an AGN, or active galactic nucleus. It's an actively creating supermassive black hole that's suppressing cooling by these 2 orders of magnitude, kind of acts as a thermostat inside of these galaxy clusters. So for those who aren't too familiar with this, I have put together a really expensive PowerPoint simulation. This is the AGN feedback cycle in a galaxy cluster. The cluster here is modeled, ICM is modeled by this blue circle here, and the black hole at the center of the cluster. They're in black, these are definitely not to scale, but just for illustrative purposes. So as the ICM contracts, it cools, and then deposits onto that central galaxy, the BCG in the center, right? Eventually, this cooling fuel star formation within the galaxy as well as black hole activity feeding onto the black hole at the center of that BCG. Eventually, these black holes can outburst through these jets of relativistic plasma that heat up the ICM, prevent it from cooling, and eventually cuts off its own fuel supply. So then, once these black hole outbursts stop, the ICM is about to cool again, repeating this whole feedback cycle. So, in case that fooled you, this is what that looks like in real life. This is this radio galaxy CSA. So in red, you see the radio jets, powerful relativistic plasma that are emanating from the central galaxy. And they're punching out holes in the surrounding atmosphere, and we see in blue the image X-rays. So I really like images like this because they show us that multi-wavelength observations of galaxy clusters are one of the best ways to see the entire baryon cycle at work in the largest galaxies. Right? And we've learned from doing these really big multi-wavelength observations that AGN feedback is one of the biggest drivers of this BCG evolution. So it solves lots of questions, but also now we have lots of remaining questions. And in particular relevance for me, I'm really interested in how has this whole feedback and cooling process, this whole cycle evolved over time. We've only recently been able to start addressing questions like these. We've only really been limited to local redshift nearby systems until we've gotten, I'll tell you about later, as these servers are allowing us to be able to probe to higher redshifts. But I don't have enough time to talk about all these things that I addressed in my thesis, but I'll talk about one of the results, which is how the conditions for triggering this cooling and feedback in the first place evolved over time. So what is the trigger for cooling and feedback in the first place? Well, if we look at where the fuel comes from, and we look at the X-ray emitting gas, you can measure with the X-ray data, you can measure thermodynamic properties, such as entropy that I'm showing you here in this plot. You can measure how this entropy looks as a function of cluster-centric radius. And entropy is just a combination of density and temperature in a way that tells you the susceptibility of this ICM gas to cool down to the BCG. Right. So what we see is that when we look at BCGs, there's lots of star formation going on. So if you look at galaxies where we have detection of H alpha emissions, so from young stars, that's shown here in the red profiles. You can see that entropy profiles reach some central entropy that's much lower than the profiles I'm showing you in black. The profiles in black are galaxies where you don't see lots of star formation going on. So this central entropy could be thought of as this measure of how thermally unstable the gas is. And if we have very low central entropy in these atmospheres, you should expect cooling and star formation going on in your central galaxy. So this is just another way to look at this. On the x-axis of both of these plots, I'm showing you that central entropy again measured from X-ray data. On the left plot, I'm showing you optical data on the y-axis measurement of H alpha emission or not. What we see is that below some central entropy threshold, you have an explosion of detections of H alpha emission in your central galaxy, and above that threshold, you see no H alpha emission. And so ICM becomes very unstable below that threshold, leads to star formation in your central galaxy. Interestingly, that same threshold, if you follow that cooling even further down to smaller scales, that makes it also to the central black hole, and you can then see that the radio wavelengths, like those jets I was showing you, for example, earlier. So below some central entropy threshold, you not only get star formation, you also get detection of radioactivity, so AGN activity. So this is actively accreting black hole. Above this central entropy threshold, you don't see too much AGN activity. So importantly here, this is really well known result that's been corroborated many times over. This has only been shown for local universe systems. This plot I'm showing you has data only from redshift less than 0.2 systems. So what I've done, tried to do for my thesis and what I'm still working on is really put a z-axis on this, the redshift, and try to answer the question, how have these conditions for sparking, cooling, and feedback evolved over time? So to do this, you need a few different things. On the x-axis, to get that central entropy measurement, you need X-ray data. To get the y-axis on this left plot, to be able to measure star formation, you need optical data. And on the right plot, you need radio data to be able to see if the AGN are active or not. And perhaps most importantly, you need to be able to find systems at different redshifts. So we define clusters at very high redshift. To do that, then I've been using the South Pole Telescope, which we heard a little bit yesterday from Jessica. So the South Pole Telescope is really great work, cosmology work. So this is using it as Z effects. And just as a little refresher, that Z effect is using the CMB photons, and as these photons travel towards us, these low energy CMB photons, as they encounter the hot ICM plasma of a galaxy cluster, they get scattered towards higher energies. And so when you look at a map of the sky as Z, what you see is a hole or a shadow where the galaxy clusters are. So this is a really cool way then of detecting galaxy clusters independent of redshift. And we can then go later on follow them up and try to figure out what the redshift is, but this then enables evolutionary studies. So a big sample I worked on for my PhD was this SPT Chandra sample. I did a lot of work on this, gathering data for this almost 100 galaxy clusters that span about 10 billion years in evolution. And so really importantly, also I did multi-wavelength follow-ups for every single one of these galaxy clusters. There's X-ray data, so we have a total about 4 megaseconds of Chandra data, so like 1100 hours. We have 39 optical spectroscopy to be able to measure star formation and looking for signs of oxygen 2 emission. That covers our whole redshift range, and also full radar coverage from things like ATCA and some SK Pathfinder surveys. So using all these different wavelengths, you can connect the entire baryon cycle in these largest galaxies over 10 billion years in evolution. So one of the things we found was that, as I've been telling you, if you look at the amount of entropy in your hot halos that these galaxies are embedded in, if that entropy falls below some threshold, you should expect star formation. And above that threshold, you don't expect star formation. This has been shown many times in the nearby universe. But what we showed for the first time is that this entropy threshold persists out to very high redshifts. Right. So as you go to the very high redshift, you can see that to the left of some threshold of central entropy, you have most of your detection lines to the left of the threshold, and above that, you have very few detectors of star formation. So this is telling us if you try to measure what that threshold actually is, there's no real significant evolution of what that value is. But this is telling us that there's a really strong, long-lived connection between cooling and star formation in your central galaxy. So I just told you about the cooling and star formation connection, but what about the cooling connection with the feedback? So this is now looking at the radio data on this bottom row, and what we see is a very different story to the star formation picture. So as I was saying before, some entropy threshold, you get detection of AGN activity to the left of it, and to the right of it, you don't get AGN activity. But as you go towards the higher redshift, what we find is that that dichotomy disappears. So it looks like there's about an equal number of detections versus non-detections of AGN activity to the left or right of this threshold, which is really weird. I don't quite fully understand it yet, but I think maybe some possible explanations, for example, mergers are another way, besides cooling, you have mergers bringing in gas to your central galaxies and feeding your black holes. As you go towards higher redshifts, merger activity increases, star formation, gas content, radio AGN changes a function of redshift as well. So perhaps this is showing us that this is not such a clear connection between cooling and feedback as you go towards higher redshifts. And this is something I'm trying to understand a little bit better. And to do that, some of the future work I've been working on is the next generation of SZ surveys. So the SPT3G survey, we find thousands of clusters out to very high redshift, about redshift of 2, back where they should be able to start virializing the clusters. And we're not going to be able to get all these 5,000 clusters and do a follow-up as I've done for the previous sample. So X-ray, optical, and radar data for every single one of those. You got to treat out a little bit, right? So my first project I'll be working on during the postdoc is this machine learning project on learning the dynamical states of galaxy clusters. So broadly, if you look at relaxed versus disturbed galaxy clusters, you can relaxed system. This is where you get lots of cooling. Disturbed is where you get inverters from, and they're both driving the gas into your galaxies and onto your black holes. So doing this in X-rays is really trivial. You can just see they look very different on the right? But we're not going to, for one, X-rays are very expensive to get, and two, we might not have X-ray telescopes in the near future flying for about the next decade or so, right? So we need a cheaper way. So what I'm proposing to do is do this with optical data alone from the ground, which is very cheap to get. And I've already kind of done this kind of proof of concept project training on simulation data, and I'll be then applying this real the SPT, the 3G sample in the future to be able to disentangle the dynamical state, what's fueling the actual black hole creation and star formation from the evolution that we see. So I'll just leave you here with the summary of what I talked about, and then I'll be happy to take any questions if there's any.
Question for Michael, 2 questions. Thanks, Michael. My name is Jen. We'll talk. So what you're doing is super interesting and obviously super cool to be pushing into the early universe. So we know galaxies are evolving. You're using H alpha to go after the star formation rates of these like PCPs. I'm a sub-millimeter person. I study sub-millimeter galaxies. We're arguing that these things are the signposts for massive clusters. You can't detect H alpha in an SMG with something like tech. I mean, you need a stack of like objects, maybe for kind of like standard observing time. So have you looked at other star formation rate indicators that might be more suitable for measuring star formation rates at earlier points?
Yeah, thank you for the question. So the question is whether we look at other indicators besides H alpha to be able to measure star formation of these galaxies. So I maybe did it too quick, said it too quickly, but the low redshift systems that I was looking at, those were in H alpha. But for our entire sample, the SPT sample from redshift 0.3 to like 1.7, I've been using oxygen 2. That covers our entire sample. H alpha kind of it gets shifted out of the optical when you go to these higher redshifts, of course, as you were saying. But yeah, I think we get to a wall. We can't really observe too much past the redshifts 1.7, 1.8, what we've been doing for these with oxygen too. So now we have to figure out ways of being able to push past those redshifts. And I think, yeah, it's like really fun because like the working group that I'm in, the SPT working group, in the cluster working group, there's also the SMG working group. And at some point they'll start, I think, converging with the protocluster community as well, converging on a redshift where we all kind of can agree on detection methods and like analyzing them too. But I'd be happy to talk more about that.
Yeah, sure.
Yeah.
One quick question. Yeah, I'll get one in. Like for your like machine learning model that you like reviewed that looks super powerful. Are you like generating like synthetic data, or are you training on your own like surveys results? Like what is the
right? So for now, what we've been training on is this the illustrative simulations. Using those and being able to have the whole merger history is really helpful. And so what we do is, because you have almost perfect compared to observational data, you have all the positions and all the magnitudes and everything. You have the whole dynamical state history. What we do is kind of do mass cuts to be able to match what we have in our sample, and also we only look at, say, like the top 30 or 40 brightest galaxies, so that we can always do that in our actual data too. So trying to trim the simulation data down to what we can see with observations, and once that's done, I'll be then applying it to the real observations. Yeah.
Let's thank Michael again. Okay, I can see this right now. Yeah. For our next speaker, we'll have Yue Hu, who will tell us very bravely about magnetic fields, even though we're not supposed to ask too much about them. He's bravely studying them in galaxy clusters. So please take it away.
Okay, thank you everyone, and I'm Yu Hu, and right now I'm a new Hubble Fellow working at the Institute for Advanced Study. Do you want to just hold it? I should do this. Yeah. Okay. So here I'm going to I will talk about the large-scale megaparsec magnetic field in gas clusters. But different from traditional polarization method, I will introduce you how to trace the magnetic field in gas clusters with the synchrotron intensity gradient. So I think the first question is, why do we need to care about magnetic field in such large scales? So here I'm showing you a numerical image from cosmic web. We know the majority of the gas or matters is concentrated in cosmic web, that's beta matrix structures, and shown in this panel here. Here, and the dense noise is where the gas cluster is located. But as we already heard from Michael's talk, in addition to the gas or the galaxy or matters, we also have radio emissions in the large scales. So if we have radio emissions, that suggests that there must be magnetic field. Therefore, if we want to have a fully or complete picture of the gas clusters, we need to combine all the three factors like the gas distribution, synchrotron emission, radio emission, magnetic field, and we can get the full picture of the cluster. So that's why it's important to trace magnetic field, because it's important for us to fully understand the physical process in gas cluster. And typically we use the synchrotron polarization to trace the magnetic field. The synchrotron emission, unpolarized synchrotron emission, is radiated by the relativistic electrons moving along the magnetic field lines. And the polarization direction of the synchrotron emission is perpendicular to the magnetic field. Therefore, we rotate the polarization direction by 90 degrees so we can get the magnetic direction. And the unpolarized synchrotron emission has been widely detected in different clusters, like here I show you, for example, here there's the Perseus cluster, and here is the Coma cluster. However, the detection for the polarization is more difficult. Here's another example that's disturbed gas cluster RxJ1314. And here the background image is X-ray emission from Chandra, and the counter represents our radio observation. In the central part where the radio emission and the X-ray overlap is called radio halo, and in the outskirts we have radio release. And the polarization has been detected for radio release because it's highly polarized, and here is polarization signal detected with the JBLA observation, and then we can use polarization to infer the magnetic direction. But the challenge comes from the radio Halo region. Different from the radio release, where the short wave and contrast magnetic field, so magnetic is quite ordered and the field is stronger. In the radio Halo regions, the magnetic is very turbulent. And for synchrotron polarization, we also need to consider polarization effect, and the turbulent magnetic field induces very significant polarization effect, which decrease the observed polarization friction. Therefore, up to now, there's no any detection of polarization in the central radio Halo regions, and its magnetic field morphology, the structure is not known yet. So here we're thinking about whether we can get rid of the Faraday rotation effect in the radio Halo region. And we're looking at the X-ray intensity, which is proportional to the density scale, and the unpolarized synchrotron intensity, which is proportional to magnetic strength. The unpolarized synchrotron intensity is not affected by Faraday rotations. Therefore, if we can use the synchrotron intensity to trace magnetic field, then we don't need to consider the Faraday rotation, and we can get the magnetic field in radio Halo regions. And here, actually, fortunately, in my research, we find actually the synchrotron intensity gradient and X-ray intensity gradient, they are perpendicular to the magnetic direction. Therefore, if we rotate the gradient by 90 degrees, we get the magnetic direction, and that provides us a new way to trace magnetic field. And such a perpendicular correlation actually comes from the turbulence in the cluster, in the ICN in intracluster medium. And when we are mentioning turbulence, we have to consider we have emission turbulence, the magnetic is strong, and hydrodynamic turbulence, magnetic is weak. So at very large scales, like megaparsec, where magnetic turbulence is injected, the magnetic field is dynamically weak. Therefore, we have hydrodynamic turbulence. But the turbulence is cascading from large scales to small scales. That means the velocity is decreasing. Therefore, eventually at the critical scale, alpha scale LA, the magnetic turbulent kinetic energy equals to magnetic energy, and magnetic field becomes significant. Therefore, at smaller scales, scales smaller than LA, we need to consider edge turbulence, and at larger scales, we need to consider the hydrodynamic turbulence. So let's firstly look at the energy turbulence, which means magnetic field is strong. And when magnetic is strong, it can shape the velocity fluctuation, shape the turbulence. And the turbulence, therefore, can be described as the interaction of anisotropic eddies. That means here the structures, like here in the numerical example, the structures are elongating along the magnetic direction. Because there's no any pressure, magnetic pressure is primarily along the magnetic perpendicular direction, therefore it's easier to elongate along the magnetic direction. And that's for the strong magnetic field case. And here, if we take let's take one structure, and we can decompose the structure into the scale parallel to the magnetic field and perpendicular to the magnetic field. And the anisotropy energy turbulence indeed suggests means the parallel scale is much larger than the perpendicular scale. Therefore, if we calculate the gradient of such a fluctuation, of the velocity fluctuation, we find actually the gradient of velocity is perpendicular to the magnetic field. It's only one perpendicular component. And the magnetic field fluctuation and also density fluctuation, they are proportional to the velocity fluctuation because that's the driver of turbulence. Therefore, we have the perpendicular correlation between the magnetic fluctuation and also density fluctuation with the magnetic direction. That's the case with strong magnetic field. And for weak magnetic field case, that's large scales, actually turbulence is not anisotropic, but it's isotropic. And but fortunately, here is dynamically weak magnetic fields tends to follow the turbulent or even non-turbulent flows. Here is another numerical example with very weak magnetic field. You didn't see any mean magnetic field in this plot. And we see the magnetic field is here aligned with the underlying structures. So that means even if we have a weak magnetic field, the magnetic effect is not significant. We still have the correlation between the underlying turbulent fluctuations and also magnetic direction. And this correlation is not just observed in the numerical simulation of just purely turbulent box, but also in the cluster emission simulation that's done by Zuhu et al. 2011. Here we can see the magnetic field is following the sloshing arm of the merging cluster. And also, it's also observed, as I showed in the earlier slide, in the cosmological simulation. Here, that's radio structures, and here that's the streamlined magnetic field. They are following structures. Therefore, in both cases, we can summarize. In both cases, with the small scales, we have emission turbulence. We can have the perpendicular correlation between the gradient and the magnetic field. And at the large scales, we have hydrodynamic turbulence and magnetic field is the dynamic wave. We still have such correlations. And therefore, if we have such correlation and we have X-ray observation and synchrotron observation, we can calculate their gradient and trace magnetic field. And here to test this method, we target on the ArcJ1314 clusters, because here we have partially detected polarization signals in the release. And here on the left is the magnetic field inferred from the synchrotron intensity gradient. And we see the magnetic field actually inferred from two different methods, actually agrees in the west and the eastern release region. But the advantage for synchrotron intensity gradient is we don't need to care about phase rotation. Therefore, with the synchrotron intensity gradient, we can complete the picture of the magnetic field in the radial Halley region. And right now, we have a full picture of magnetic field structures in the cluster. And also, I wanted to mention another interesting cluster is the Yergol cluster. It's the largest cluster at redshift around 0.7 and H7. And similarly, only for earlier studies, only the polarization is only detected in the release region. And there's no any detection of the polarization of magnetic field in the radial Halley region. But right now we have meerkat radio observation data, and we have the synchrotron intensity gradient method, and we can get the full structure and the full magnetic field geometry in the Yergol cluster. And then let's add back to maybe the second slide. It can provide us actually more information to understand the clusters. With GWST, the image is the background image is GWST observation. It can tell us the distribution of galaxies, and the blue shadow area is the X-ray emission from emitted by Chandra observation. But right now we have more information. We can use the Pathfinder meerkat is Pathfinder telescope of SKA. It can tell us the distribution of non-thermal gas and the radio emission. And if we use a synchrotron intensity gradient, we can also get the structure of magnetic field. And the structure of magnetic field is indicative of the gas flow in the gas clusters that can help us to understand the gas merger process and can tell us more information about the cosmic acceleration and the generation of synchrotron radiation in gas cluster. So I'll finish my talk here and I'm ready to take questions.
Question for you.
Are you making any robust predictions that you can validate on the magnitude of the polarization, not just the direction? And what sort of uncertainties do you have on the direction of this correlation?
Yeah, that's a good question.
Could you repeat the question?
Okay. Okay, repeat the question. So the question is whether I can get some information on the magnetic strength and what's the uncertainty in the magnetic field orientation predicted. So here for the first question, like the magnetic strength, right now we don't have the information on magnetic strength. It's more complicated. My work right now can only get the direction, can only get information on magnetic direction. It's more important to get the magnetic strength, but I think the radio emission, it must contain the information on magnetic strength because the luminosity or the brightness of synchronous emission is correlated with magnetic strength. Potentially, we can also use like the machine learning to find the information on magnetic strength, but right now I don't know whether it will work. And for the uncertainty here is, of course, we have observation uncertainties like the radio source. Radio source, they are not correlated with gas. They are not correlated with turbulence, of course. So when we are dealing with the synchrotron map or the radio observation, we need to consider how can we robustly remove the radio source and to get a more robust observation predictions.
Time for one more question? Yes, please. So the source down at the bottom, that corner, or the striations that we see on top of it, same the ones up there. What are we supposed to do in the process of seeing there?
What do you mean this one?
Yeah, that object right there, you see has the very fast lines, the striations. No, this one? The white. The white source right there, and then up. Here goes my laser pointer. Okay.
Now you can just point to it. I need you can just walk up to it.
There we go. Hold it down. Right there. The striations. Same with this guy up here, similar striations.
Oh, okay. That corresponds to the radio relief regions here. That's where the shock front is.
It is shocks.
Yeah,
Okay.
shocks. So
Okay.
shock will compress.
Yeah.
So if the shock is perpendicular to the radio axis, the gas is falling along the magnetic radio axis. So here it shocks, the magnetic is compressed and
Right. Okay. Okay. It's a compression to the shock.
Yes.
Let's thank you for a great talk. Next up, we have Viraj Pandya, who's a NASA Hubble Fellow at Columbia. He's going to be telling us about new puzzles in galaxy formation, in particular about how we go from the cosmic web to the origin of the Hubble sequence. Take it away.
All right. Thanks, Rohan. So hi, everyone. My name is Viraj Pandya. I'm a Hubble Fellow at Columbia. This is actually my last symposium, so I wanted to take a second to thank the leads for overseeing this amazing program, which really gives all of us the independence to pursue the research that we're really interested in. And so I'm very excited to summarize some of the research I've been doing over the past 3 years. I'll start with my theoretical work, which is really motivated by movies like this one, which shows the large-scale 3D clustering of galaxies centered on the Milky Way. It's really important to understand galaxy clustering on a large scale because it's one of the best ways that we have to answer this fundamental question that drives the research of Hubble Fellows, right? How did we get here? So let me split this question into 3 smaller ones. What is the universe made of? What were its initial conditions? And how did galaxies like our own Milky Way form? These 3 questions are actually, at the heart of a large collaboration that I'm a member of, called the Science Collaboration on Learning the Universe, which Karthik Iyer here is also a member of. And we want to infer it's not just the cosmological parameters that tell us about dark matter and dark energy and so on, but also the millions or potentially billions of parameters that encode the initial conditions of our universe. So by that I mean the distribution of the phases and amplitudes of the initial density perturbations that eventually gave rise to our local volume, right? The exact configuration of galaxies that we see within a couple hundred megaparsecs centered around the Milky Way, as shown with this, this projection of density from the 2 mass galaxy parallel. So the way that some of my colleagues in this collaboration have approached this is they've devised a very sophisticated algorithm to generate simulations of the local volume that are fully Bayesian and that are able to use all of the available data that we have on galaxy clustering to then constrain the posterior on these millions of parameters. It's very challenging to do, as you can imagine, but if you can do it, you can make really cool movies like this one, where within the volume where we actually have data on galaxy 3D clustering, the simulations drawn from the posterior are actually very well converged, constrained, but beyond that volume, a couple hundred megaparsecs around us, the simulations are not very constrained. And this is about to get much more interesting because NASA is spending billions of dollars on mapping billions of galaxies out to much larger distances than what I just showed. And while this is very exciting, we actually don't have the tools to leverage all the information that these stories are going to provide, because we don't understand how galaxies trace the underlying invisible web of dark matter, right? We don't have a physical forward model for going from the density distribution of dark matter to the actual distribution of galaxies that we observe, like luminous objects tracing out the dark matter. Fortunately, we have other data, not just luminous galaxies. You heard about yesterday afternoon and earlier in the session, right? We have lots of data from many different facilities on the spatial distribution and the thermodynamic state of gas within and around galaxies. And it's really, I think, we need models that can account for how gas flows into and out of these galaxies and their surrounding gaseous atmospheres to constrain a lot of the degeneracy in our galaxy formation models. And really start to use galaxies to probe the kind of cosmological questions that I posed earlier. So these kinds of challenges, of course, how do you translate these kinds of beautiful cartoons to ideally Bayesian models with which you can do inference, right? So one way, of course, is to do simulations, and I've used, for example, the fire simulation over the past few years. This is actually a pretty good comparison to this cartoon here. As you can see, lots of gas flows, they make detailed predictions of the properties of galaxies, but they're very complicated, right? You don't automatically obtain an understanding, an explanation for why the gas is flowing the way it is in these simulations or in reality. And they're very expensive, right? You can't run the millions or even thousands of these that you need to do the kind of proper Bayesian inference that we want to do. And so one of the big outputs of my whole fellowship was actually translating those nice pictures and movies to a simpler, interpretable, physically motivated framework, which is tracking the flows of mass, metals, and energy into and out of galaxies and their surrounding medium. And it's been on the news for 50 years. And the new thing that I really added in is these new energy flow differential equations, which really let us give us a way to couple feedback energy from supernovae and black holes to how that feedback couples to the circumgalactic medium, heats it, stirs turbulence in it, suppresses its cooling, and this in a way provides like a large scale circumgalactic medium based regulation of small scale star formation. So these models are very fast and they're very interpretable. And so with my student Chris Carr, we've been asking this question. Why are galaxies so inefficient at converting all their available baryons into stars, right? And so in galaxy formation, all of us love this empirical correlation between the stellar to halo mass ratio and the dark matter halo mass. And so on the left here, I'm showing you with these purple lines, we have we're varying in our model what is considered to be traditionally a very important physical parameter that says how much gas mass you have to get out of the galaxy so it doesn't turn into too many stars. And when you actually connect the dots and you couple both the energy and the mass flows between the galaxy and the circular medium, in this new framework, variations in the mass loading are actually the models are very sensitive to that. It's really variation in the energy content of the wind, which sets its capacity to heat and suppress cooling in the circular medium that the model showed a lot of sensitivity to. And so this is one of the puzzles, right? How do we observation distinguish between this mass loading original old paradigm for feedback and then this new energy loading paradigm? I don't have the answer yet, but it's going to be an exciting area of future work, I think. Something else that I've done is I've shown over the past year that you can actually use these simplified models to explain and in some cases emulate the physical processes that occur in these very complicated numerical simulations. And one of the questions that the galaxy community is interested in is, for these atmospheres around galaxies, what causes them to undergo these phase transitions over cosmological timescales, billions of years, right? So we think, in this one example of the Milky Way galaxy evolution, we think at early times, the Milky Way's atmosphere was very cool and turbulent, high redshift, and then at some point, depending on your recipes for feedback and cooling and so on, it underwent this phase transition, this thermalization, where it's developed this million-degree Kelvin atmosphere that we see around the Milky Way today in X-ray absorption and emission. Something else with Mark Voigt, we've been asking how, if you explicitly account for the gravitational potential energy of the circular medium and the dark matter halo in which these galaxies are evolving, how does that atmosphere respond to feedback and cooling? And so we've been doing an accounting of all those possible mechanisms, and we think that the CGM actually goes cycles of expansion and contraction, and this could lead to new observables that can help machine these kinds of models. So all this stuff is very interesting, but it really, the models are a dime a dozen, and the question really is, how do you enable, the kind of Bayesian inference that we really want to do? And so over the past year, I've been putting a lot of work into this new framework that we're calling Sapphire, which is written in one of these lightweight machine learning libraries called JAX. And it really enables a lot of new things for galaxy formation physics models. So I'll kind of quickly step through these things. So to the best of my knowledge, there is no model of this type where you can run on multiple GPUs. And so for the first time, actually, we can get more than 100 times speed up relative to solving these differential equations for one galaxy at a time sequentially. Something else, for the first time in the 50-year history of models of this kind, we get the full Jacobian and Fisher information matrix computed exactly and rapidly in a fraction of a second, so that we know the sensitivity of the model's outputs as a function of redshift with respect to variations in all of its three parameters. This is useful because it gives us insight into the behavior of the model, but it also lets us take smarter steps in high-dimensional parameter spaces when you're trying to do like Monte Carlo type inference. We're also adding new physics into these models, so I'm lucky to be the PI of a large NSF AAG grant to add satellite galaxy differential equations into the Sapphire. With my student often gave a live, we've had a preliminary implementation. We're making predictions for the satellite stellar mass function of Milky Way analogs in blue, as well as for isolated field LMC mass hosts, which is going to be testable with Roman in a few years. With my colleagues Brian Johnson and Sophie Gudmani, we've also been adding black hole feedback, which is required, as Michael just mentioned. Without it, we would form too many stars in massive cluster galaxies. So that looks promising. And then with Lucas Buchanan, we've been trying out this hot new way of doing inference, where in many cases, if you're trying to combine lots of different data sets as your constraints, it can be hard to define an explicit likelihood. But if you can just generate lots and lots of realizations from your model for different parameter combinations, you can train a neural network to learn the mapping between your parameters and your model outputs, and then you can feed it the actual observations. Eventually, you get posteriors out on your model parameters, which is neat. So I can say a lot more about all this, but in the last few minutes, I want to just advertise one of the things that I'm working on very briefly. So that is constraining the 3D shapes of higher redshift Milky Way progenitors, installing the observational side into VPOC. So we've all seen movies like this, right, where dark matter is initially collapsing along sheets and filaments. But something that I think is missing in our discussion is that dark matter halos of lambda CDM actually initially start out elongated. Right, and this is because it's forming along these filaments of the cosmic web. And in very high resolution simulations, it's also predicted that the galaxies in these elongated halos should also be very elongated at early times. And so here's two tracks from one of these galaxies. In these simulations, the red is just at early times when the dark matter is dominating the potential. And so in this flattening elongation space, you have galaxies starting out relatively elongated, like cigar shaped. And then over time, as they build the baryons and the centers, the stellar distribution becomes a disk types that we are more familiar with. And so my amazing colleagues Farhan Hassan and Hawan Zhang, we were going through the TNG simulations and quantifying the environments and shapes of halos and galaxies. We measured the sigma fill parameter, which when it's very small, the means are forming along a very small tendril-like part of the cosmic web. And so this is now sigma fill as a function of stellar mass, color-coded by the elongation fraction through redshift. So you can see, as you move towards higher redshift, it's the low mass things forming along these small tendril-like filaments in the cosmic web that are initially elongated. And that's also where we find the elongated stellar distribution as well. This is a nice story, but it's very evidence for this in the data. That was the motivation for this paper that I led earlier this year with the sensational title Galaxies Going Bananas, right? Where we used deep imaging from JWST to characterize the shapes of galaxies at high redshift, low mass, including Milky Way progenitors. And we plotted the predicted axis ratio as a function of projected size, and we found this interesting distribution, which does equal a banana. which is the motivation for the title. And so there's a deficit of rounder high redshift orbs, right? And a lot of things piling up with small B over edge on things, right? So these are some examples of these things. Our main point is that there's way too many things that look like this. So if you want to preserve isotropy, not all of them can just be discs seen from the side. Right, so our preferred interpretation of many possibilities is that galaxies are not starting out like spheroids and disks like we imagine, like my models, for example, assume. Instead, we think they're significantly flying along a second axis. So they're like totally ellipsoid, which are much more likely to see with a long axis in projection, kind of like this clicker, which only very rarely you'll see it along the long axis down the barrel. Skipping to a lot of basic analysis, but one of the most striking things about this is here is the relative contribution to elongated galaxies in blue as a function of redshift of these two stellar mass bands, and you can see that as you move towards high redshift, these things are dominating at 50 to 80% level. Right, so you should be thinking, how can this fit into our picture of galaxy formation? So let me try to address that in relation to the Hubble sequence. Right, I'm going to introduce this, right? But here's how the elongated galaxies fit in. So they think galaxies start off elongated because they feel the influence of their environments. And then they undergo star formation, inversions, and so on, which leads to the formation of a compact central spheroid. And it's around that spheroid that we think, the disk is grown eventually. One last thing is, this has another very striking prediction, right? So in this story, if this is true, then these galaxies should be very strongly aligned as they trace out the limits of the cosmic web in which they're forming, kind of like light bulbs along a string. So my advisors in 2019 at the time, we predicted a very moving signal in the data or in mocks, but we didn't see anything in deep candle imaging at the time. And most recently with Avi Loeb and some of the Sears architects, we actually revisited this in the context of lensing, which is very sensitive to the assumed intrinsic shapes and alignments of galaxies. And using a different way of averaging what we use of galaxies, we actually do find several regions of JWST blank deep fields where we see strong alignment patterns, in many cases like polarization type patterns as well. So there's many possible explanations. Could be, there could be a protocluster or filament of actually 0.75, which could be causing some of these alignments via lensing. I mentioned the hypothesis for intrinsic alignment. There's systematic, but we can rule those out because we use the stars in the foreground as the null test, but they shouldn't be sheared or aligned. So a lot more to say about that. Last thing, teaser, one slide. The thing I'm working on now, I think the frontier for this kind of science is really to constrain the stellar orbits in these systems. If these things truly are intrinsically cigar or surfboard shape, the stars cannot be on circular orbits. This is borderline impossible with current facilities. I'm trying, but it's going to be possible with the ELT. So stay tuned for papers from Hollow Wednesday and myself about this. So I'll leave my summary slide up and I'll just say, there's lots of questions, lots of puzzles, these and others, and I think the work that I'm doing to bridge both the observational and theoretical sides is going to be, I think, crucial in the future to continue to get insights and uncover new puzzles. Thank you very much.
Okay, we have time for one quick question. Yes.
So I think this is one of your earlier slides where you said that where you were trying to figure out why star formation efficiency is so low. Does that apply to Milky Way-like galaxies? Because on the star formation side, one of the things we're looking at is sort of on a molecular cloud scale, why is the efficiency so low? But are you saying that it's actually a much larger scale, so we shouldn't be looking at molecular cloud, we should be just looking at a much bigger picture?
Great question. So the question is, on Milky Way scales, is the low star formation efficiency due to like these large scale effects or these small scale GMC scale effects? And I think the answer is they're not mutually exclusive, and we're actually trying now to, I didn't talk about it, but we're putting in models for these small scale physics, GMCs and cluster formation, things like that. And we're going to have to marginalize over the parameter space for both these large scale and small scale effects, which we could do in this new framework to see what constraining power the data has.
Thank you so much, Raj. That was a great job.
Okay, for the last talk of our session, we have Dallas Goodke joining us remotely. We can see your slides, Dallas. Dallas is going to be talking to us about dwarf galaxies and all the things they can teach us about our universe with a focus on self-interacting dark matter. Take it away, Dallas. We can see your slides.
Thank you, Rohan. And same for me. This is my last symposium, so I want to take the chance to, first of all, say I'm sorry I can't be there in person. It's a real shame because it's been so fun all the last few times, and thanks to the leads and to all the other Hubble Fellows. So today, I'm kind of going to do the opposite of what Viraj just did. I'm going to focus not on all the things I did in the last few years, but just on what I've been working on most recently. So that's self-interacting dark matter and dwarf galaxies. So if you don't know why they're interesting or important, let me just jump right in and talk about the relevance of dwarf galaxies for researching dark matter in general. So dwarf galaxies do describe some of the tightest constraints on dark matter models, as this plot here shows, where we see that a lot of different dark matter models, whether different feedback models or different warm dark matter models in this case, all pretty much make the same predictions at galaxy masses higher than 10 to the 9 or 10 to the 9.5 here, but really start to show distinctions at the very low mass end of dwarves. So this is a really amazing way to study a variety of dark matter models in dwarves. But we need to know about dwarves, and especially these very low mass dwarves, which is actually not as easy as it may sound. And one of the places where these distinctions can be made is right at the centers of dwarf galaxies, which in the case that you might have heard about called the cusp core question. But it also simultaneously can constrain baryonic models, so feedback models in galaxy formation physics of what things are necessary to prevent star formation and feed back energy into the baryons in the galaxy. And so, as I said, really it's the smallest, it's not only just dwarf galaxies, it's actually the smallest dwarf galaxies that provide these constraints. And the problem with that is that up until now, we really only have data for less than 100 of these dwarf galaxies that in this case, I'm doing an observational comparison. So I'm showing a V-band magnitude greater than -10. So we have very little observational data currently, but what's amazing about studying dwarf galaxies at this point in time is that we're really expecting an explosion of dwarf galaxy detections in the now and in the very near future. And so I'm just listing some of the different telescopes and instruments that have already come online, including, of course, JWST, and Euclid was launched not that long ago. And then very, very soon in the next year or so, we'll be getting even more facilities, full telescopes and other instruments. And there's also longer term projects that are going a little bit more into the future. And so this is just one plot from a prediction from the Rubin Observatory. So after somewhere between 200 and 1,000 visits, we are expecting to see and to up our numbers from less than 100 dwarfs at this magnitude to anywhere between 1,000 to 100,000 of these types of dwarves. And the reason that we don't know, of course, exactly this number is because we actually don't even know the shape of the luminosity function of galaxies at this very low mass end to such precision because we have so few numbers. So it's a really exciting time to study dwarf galaxies. And at the same time, because we're finally getting data on these small dwarfs, it's a really exciting time to use this to study dark matter models. And so I have been very recently studying self-interacting dark matter, and I will not only explain to you what that is, but also why it might be an interesting alternative dark matter model, specifically in the context of dwarfs. So this is a dark matter profile showing going from the outskirts towards the center of a dwarf galaxy. And depending, so the two blue lines here are our standard cosmology, lambda CDM, both with baryons and without. So DMO stands for dark matter only. And as you can see, they both kind of predict the same profile shape, which is well fit with this Navarro-Franken-White NFW dark matter profile. And then if we turn on or change our cosmology to a self-interacting dark matter universe, this prediction changes quite significantly. But as I will explain, this is only one prediction because actually self-interacting dark matter is a family of models rather than a single model. So there's different parameters that can still be set and that are unknown. But what I want to show in this slide is just the connection between the dark matter profile shape and the rotation curve, because I'm going to be talking about them kind of a little bit interchangeably throughout this talk. So dark matter profiles are, of course, just the density of dark matter as a function of radius within the galaxy. And then this can be transformed into a rotation curve. So this dark blue line and this dark red line, if you transform them into what the rotation curve of this galaxy looks like, you get this distinction here. And so in this case, a flatter central density produces a shallower slope in the inner sections of the rotation curve. Just to take that with us. And I've already hinting here at what we're going at, because the dots here are data from observations of a specific dwarf. So there's definitely observations that have a much shallower inner rotation curve than what our standard cosmology would predict. And this is really kind of the heart of the problem, or the questions that we have around dwarf galaxies and dark matter. So it's not that observed dwarves and standard cosmology, lambda CDM dwarves, just predict different rotation curves. What's actually happening is that we're predicting a diversity of rotation curves. Sorry, observations are showing a diversity of rotation curves, whereas lambda CDM, as our standard cosmology model, is predicting not that much diversity. So I'm showing this here with 4 different observations of rotation curve shapes from different dwarf galaxies. And as you can see, some of them are kind of peaked too early and then flatten out. And a lot of them, but not all of them, are shallower than what we would expect from a classic simulation. And this can be summed up also in these 2 plots, where if you look at a bunch of dwarf galaxies in your lambda CDM cosmology, the different circular velocities, in this case measured just at 2 kiloparsec at a fixed physical distance, have quite a tight predictive area, whereas our observations are showing a much broader range of things. And so this is really kind of the heart of the problem that we're trying to solve when we go in search of potentially alternative cosmologies and alternative dark matter models to try and understand why observations are showing this huge diversity. So enter self-interacting dark matter. And so why is this an interesting theory in this context? For one, it's just something that I think kind of sort of intuitively makes sense. Like our standard cosmology, we assume that a single dark matter particle doesn't interact with another dark matter particle other than gravitationally, right? And so we've created these dark matter particles in our minds that just have mass, don't do anything else, and just fly around and never interact with each other. And this just intuitively seems odd that they wouldn't have some form of interaction with each other. I mean, that's just my personal opinion, I suppose. So self-interacting dark matter is a model where we say, well, how about we expect there to be an interaction? What kind of interactions are possible, and what would we need to assume to make such an interaction possible? So of course, that's why it's a family of models, because how they interact with each other is pretty much an open question, but it requires invoking a new gauge boson that would facilitate this interaction. And then the question is, how strongly do they interact? Do they just scatter with each other, or can they annihilate each other completely? And so this is where research is currently trying to study these different questions. So the most common parameter in a lot of SIDM, as it's called, self-interacting dark matter models, is the scattering cross-section. So the strength of the interaction physically in a scattering scenario between two dark matter particles. And as the field has already moved on a little bit, we've kind of already decided that there can't be a constant scattering cross-section that's just a fixed number. And so people have introduced a velocity dependency. So that means that you have two dark matter particles, they're moving at a relative velocity to each other, and the relative velocity of the two particles dictates the strength of the interaction between the two. And so that's when you hear talk about a velocity dependent scattering cross-section, that's what that is. And so we can already see here from some work from a few years ago by Camila Correa that depending on how you set the sigma, so this scattering cross-section, if you look at different predictions for the dark matter density profiles, you can get quite a variation. Problem with a lot of SIDM work to date is that it's dark matter only simulations. So you exclude all these questions about baryonic physics that have actually been kind of what's been dominating galaxy formation studies in the recent years. And so my work has been using this model, Lyra, that I've been developing in the last few years to study dwarf galaxies, that has incredibly high resolution and includes a huge array of very small scale detailed baryonic physics, including multi-phase ISM, individual stars, individual supernova, chemistry, star clusters, supernova-driven outflows, all of this rich, detailed baryonic physics. And what's special, I guess, about this combination is that it's not that people just aren't interested in baryonic physics in combination with self-interacting dark matter. It's that self-interacting dark matter simulations are computationally expensive. And so doing this with baryons in a Milky Way sized galaxy is actually pretty much prohibitively expensive. And so my model and my dwarf sit at this sweet spot where actually running the two together is computationally feasible. It's actually pretty much one of the only places where SIDM simulations can be run in a complete baryonic physics universe. So this is what I've been doing. And this is already the first result here. So these are the subhalos of a dwarf galaxy and the shapes of their rotation curves in standard versus SIDM. And you can already see here that you do get a higher diversity of rotation curve shapes rather than them all increasing together and then flattening out. We already see some variation here. And the reason, I mean, this is not just me, like people have been studying SIDM and understand that this can happen in certain scenarios. And what's actually happening is that you first create this dark matter core, so this flat profile in the center, and then certain processes such as falling into a larger galaxy can actually cause an instability and cause that core to collapse. And it actually collapses to an even denser or more peaked rotation curve than a lambda CDM cosmology would predict. So that's how you can create this diversity of rotation curves. And so I'm just showing here the of 6 that I picked out of the core collapsing subhalos in the model, where you start at, say, redshift 1 before they've fallen in to the larger galaxy, where they're still flatter, and then in the centers here, they're flatter. And then as they collapse, core collapse, they actually become even more peaked than a lambda CDM prediction. And another way of showing this is to look at this parameter space opened up by the rotation curve. So Vmax is the peak velocity of the rotation curve, and Rmax is the radius at which that peak occurs. And then I've tracked different satellites in my simulation backwards in time. So the red is earlier in the universe and blue is later in the universe. And as you can see in the SIDM simulation, we have this different trend of tracks where many of the halos are decreasing their Rmax. So the location, the radius at which the rotation curve peaks moves to smaller radii over time. And so this is happening continuously for a subset of the halos in SIDM. Another thing, so that's the diversity of rotation curves question. But of course, now that these simulations exist, I can try to look at some other things as well, because they include baryons. It's interesting to look at how the new dark matter potential alters the baryonic underlying distribution. So one thing I can look at is for the non-core collapsing halos, what's the core size as a function of mass, in this case of the satellites. So there is a power law relation between the two. And then I've been talking a lot about the satellite galaxies. So the last two slides.
One more minute. Could you wrap up in like a minute?
Yes.
Thank you.
Is to look at the main halo. So we do get a variation in the star formation history of the same galaxy. And then we can also look at the gas and the stellar distribution. This is at redshift 0. So you can see there's a much wider gas and stellar distribution in the SIDM universe. And we can look at this quantitatively if we look at the stellar surface density, that there's actually a real observable reduction in the central density of the dwarf. So this is the work that I've been working towards, trying to understand if we can have, if there's really some smoking gun observational evidence for SIDM in observed dwarfs. And so that's my recent research using both my high resolution baryonic physics dwarf galaxy model, and bring that together with this whole question of alternative dark matter scenarios and how we can use this explosion of dwarf galaxy data in the near future to constrain all these open questions. As usual, my model is still under development. If you're interested in working, I'm happy to collaborate with anyone who's interested. So thank you.
Thank you so much. Let's hear it for Dallas. Yeah, unfortunately, we don't have time for questions. I encourage you to please message Dallas on Slack about Lyra and all these great dwarf galaxy results. Before we adjourn, we have a couple of quick announcements. Andy, you can go first, followed by Tamisha.
So back here for the next session at 2:20.
We just want to let you guys know about AMP Up, which is a fellow-driven program. It's not just Hubble fellows; it's a bunch of other fellows together, where we have mentor-mentee groups, and it's a sort of collaborative mentoring process. And anyone's welcome to join. We'll have a presentation about it at the open mic, with maybe some something that Justin and I will come up with. And then there's also the Hubble application feedback program, which again, anyone is welcome to join. So I think the idea is any prospective applicants send us the applications, we share them with with any other fellows, they will grade it, they will give feedback and send it back to the fellows.